Welcome back, students. In this video, we are going to look at rate equations, especially the factors that affect the rate equation in organic chemistry. Let's start with a quick reminder from Gen Chem 2 of what a rate equation is. So a rate is going to be how quickly a reaction is going to happen. And when we look at the rate of reaction can depend upon a couple of things. And first, we're going to look at the rate equation. In the rate equation, you have this K, and that K is your rate constant. This constant is specific for every reaction. So it's not something that is generalized, right? It's specific for reactions. Then we have the reactant or reactants. In this case, remember that when you see that reactant in brackets, what that actually means is the concentration of that reactant. If we consider our rate equations or our reactions involving species that we'll call A and B, this first rate equation down here is looking at how just the concentration of A impacts the rate as well as the rate constant. This would be called a first order rate equation. In this first order rate equation, what happens is if there's even another compound in the reaction, it does not even affect the rate. It's just A that affects the rate. If you have both compounds, so A and B, affecting the rate, that's called a second order rate equation. And there's other ways that you could have a second order rate equation, but they're not typical in organic chemistry and the reactions that we're going to look at for rate. And then the third one is, see how you can have a squared next to a certain concentration? This would be an example of a third order rate equation. And so when you're looking at order, really all you're doing is you're considering how many species are involved in the rate equation and if there is an exponent on one of those species. So first order, there's one species. Second order, there's two species, or technically, I'll just show it to you. You could also have something like this, right, where you have A squared. And then the third order, you have A twice and then B all involved in the rate equation, right? So you get third order. Most of the rate equations that we're going to look at in the future are going to be the first order rate equation like this and this second order rate equation. So that will be our focus in organic chemistry for the remainder of the semester. I want to talk now about the things that can affect the rate constant. There's three things that I want to look at in particular. The first one is energy of activation. I'm going to bring your attention down here to an energy diagram. And remember that in your energy diagram, you have a y-axis. This one here is potential energy. And then your x-axis is your reaction progress. You might see a different name for reaction progress, like reaction coordinate or something like that when you are looking at other resources. And that's perfectly fine, right? There's multiple names for it, but really it's just tracking the progress of the reaction. When we consider the energy of activation, remember that here is the reactant's energy, and this is where your products are. The hump that you have to get over is from your maxima here down to your reactants. So this amount of energy is your energy of activation. It's what we need to get over in order for the reaction to occur. If that energy of activation is quite high, then it's going to be difficult to get over that hill. If the energy of activation is lower, it's going to be easier. Let's look at that. Here I have two more diagrams where the y and x-axis are the same, and I'm illustrating that you have a smaller energy of activation for this first one. And for the second one, you have a larger energy of activation. And I just like to draw that line from the reactants to the middle of that first, and in this case only, hump, that hill, just so that we can better grasp that what we're comparing is the energy of the reactants to that high energy maxima. Those energy of activations are definitely going to have an impact on the rate. Something that has a smaller energy of activation, well, is if molecules collide with enough energy to get them over that energy of activation, then the reaction is going to happen, assuming we're talking about a collision type reaction, which is easiest to imagine, so that's the one I'm going to talk about. Then your large energy of activation, what'll happen if your molecules collide, but they don't collide with enough force to get you over that hill, then they just slide right back down and they stay reactants. So that size of the hill, the size of the energy of activation, has a huge impact on the rate. The higher the energy of activation, the less likely it is for that reaction to happen successfully. Let's consider how temperature can impact the rate. As temperature increases, molecules are going to have a higher kinetic energy. And if we're looking at a reaction where molecules collide in order for that reaction to happen, imagine these molecules that are moving have to come and hit one another. When they hit each other, they have to overcome that energy of activation in order for that reaction to happen. So in this case, if you have something that's a reaction that's running at room temperature versus a reaction that's running 20 degrees above room temperature, the higher the temperature, the more the molecules can move, the faster they're moving, the greater their kinetic energy is. And then when they collide, they really collide and they get over that energy of activation. Whenever I think about these molecules colliding, I always imagine like children in a ball pit or something like that. Like imagine you have some lethargic kids who are not excited to play, right? Those are your molecules that are at a low energy. But then you have some kids who are very excited to play because it's a birthday and they just had cake and they're with all their friends and they're like bouncing off the walls. That's what happens in my brain when I'm thinking about molecules having enough kinetic energy to result in a reaction, right? If they have a higher temperature, they can bounce into one another and end up overcoming that energy of activation and have a reaction occur. The third thing that can impact the rate of reaction is something called sterics. If we go back to that idea of collision, right? So here's a molecule that's moving, and here's another molecule that's maybe also moving. When molecules collide in a reaction, if this one collides, say, this direction, the reaction is going to happen. But if it were to collide, say we have a different one, if it were to collide from this direction, then no reaction would happen. This is called sterics, or a steric consideration, meaning that it depends upon the type of collision and where the collision is occurring, whether or not a reaction is going to happen. And we're going to see this type of issue in our next chapter's worth of videos, where we start talking about substitution reactions, where there's a very particular collision that needs to happen in order for a reaction to occur. But I just don't want you to think that whenever any molecules bump into one another, that magically a reaction happens. Sometimes there's other considerations that need to be taken into account. The last idea I wanted to talk about is catalysts. Catalysts are something that we're going to use commonly throughout organic chemistry, but you know what? You have seen them before in biology and you have a misunderstanding of what a catalyst is. Like I'm going to say about 90% of you do. A catalyst is something that speeds up a reaction and it is not consumed. Here's the key. This is the misconception. A lot of biology teachers will say something along the lines of, your catalyst lowers the energy of activation. That's not really what's happening. Your catalyst provides a different pathway. And that different pathway, that just happens to have a lower energy of activation. If you say a catalyst lowers the energy of activation, the reason that's false is because you're assuming that it's the same pathway. and that you were just taking that pathway and lowering its energy of activation, and that's not what's happening. We're providing a different route by utilizing a catalyst that just happens to have a lower energy of activation. We still get to the same products at the end. We just used a different way to get there. So imagine it's like, instead of walking over the mountain, you walked around the mountain, right? Over the mountain is your uncatalyzed pathway. Around the mountain was your catalyzed pathway. So you still got to the same point. You just took less energy getting there because you chose a different route. Let's wrap up. In this video, we looked at rate equations and we talked about the factors that affect rate constants. We discussed energy of activation, temperature, sterics, and then we revisited catalysts with a correct definition. Thanks so much for your attention. This is Katoni signing out.